this is a class of vector calculus. Okay, and in this class or in this section we deals with the important term. This is integral transform. Okay, and this is also known as vector calculus or multivariate calculus. Right, this is also known as multivariate calculus. And in vector calculus we know that there are three types of integration. The first type is the line integration. This is over C, or this is also known as contour integration over C. And we get the second type of integration. This is the surface integration. This is over S. And the last type integration is the integration over V. This is the triple integration or volume integration. Right? This is line integration. This is surface integration. And this is volume integration. We deal with these three types of integration. And integral transform means we transfer one type of integration to another type of integration. Like we transfer surface to volume or volume to surface, and another surface to line or line to surface. To transfer this integration or integral transformation, we deal with three main theorems. The first is Gauss Divergence Theorem, and this theorem gives to transfer the surface integration to volume integration or volume integration to surface integration. And in Stokes' theorem, this is transform from line integration to surface integration. Also in Green's theorem, they transfer line integration to surface integration. These two are the same theorem, and Stokes' theorem is the general form of Green's theorem. This is the general form of Green's theorem. In this section, we discuss these three theorems one by one together with an example or an important application. And in this first class, we deal with the Gauss Divergence Theorem together with an application. Now, the Gauss Divergence Theorem or simply Divergence Theorem is, if V be the volume bounded by the closed surface S. Okay, so this is the volume, and this is bounded by the closed surface S. This is S and this is V, right? And F is a vector valued function with continuous first derivative. That is, if we take F vector, this is F1i plus F2j plus F3k cap, then del F1 by del x, del F2 by del y, and del F3 by del z, and other derivative, that is del F1 by del y, del F1 by del z, etc. All are the first order derivative with respect to x, y, and z, and these all must be continuous. Okay, this is the meaning of continuous first derivative. And then divergence theorem states that triple integration over V div f dv, and this is also can be written as integration over V div f dv, right? And it may be written by a single integration and over V. This means the volume integration, or this means the triple integration. Okay, there is no difference between triple integration and single integration. This means triple integration because this is over the volume V, right? And this is equal to double integration over s f dot n ds, and this is also written as integration over s. This means double integration over s f dot n cap into ds, right, where n cap be the unit outward drawn normal. Unit outward drawn normal means, let the surface is like this. This is the surface, okay, and we drawn a unit normal to this surface, and let this is p and this is the tangent. This is tangent. So the perpendicular to the tangent is like that, and this is the direction of n. This is outward direction, and outward normal is taken to be positive normal. Okay, so this is n cap, and this is the positive normal of the surface, and this integration can be written also as integration over s f dot ds. Here s is also a vector, okay, and here we write ds vector. This means n cap into ds. Here s is scalar quantity, but here s is vector quantity, because we know that there is direction and magnitude both for the surface. So ds must be vector quantity. Okay, so this statement can be written in the form this type. In this problem, it is given that evaluate double integration over s 4x I cap minus 2y square j cap plus z square k cap dot n cap ds using divergence theorem, where s is the surface bounded by the volume x square plus y square, this is equal to 4, z equal to 0 and z equal to 3. Clearly this volume is a cylinder, okay, whose base is a circle x square plus y square equal to 4, and this is from z equal to 0, that is xy plane, and this is z equal to 3 parallel to xy plane, and the volume looks like, if we draw a cylinder first, right, this is cylinder, and this is the lower face and this is the upper face of the cylinder, and let this be origin, and this is z axis vertically upwards, this is x axis, and this is y axis, and let this, okay, and sorry, this is straight line. This is yz plane, this is z axis. Now we have to use the divergence theorem and evaluate this integration. Clearly this is the surface integration, so this side is given. So f is given by 4x I cap minus 2y square j cap plus z square k cap. Okay, now if we use divergence theorem, then we have to find out divergence of f first. So df, this is equal to del x of 4x plus del y of minus 2y square plus del z of z square, and this is 4 minus 4y, and this is 2z. This is divergence of f, right? Now we use divergence theorem and get double integration over s f dot n cap ds. This is given, and this is equal to triple integration over v d f dv. Here df is 4 minus 4y plus 2z, and dv, this is equal to dx dy dz, because any volume element is look like a rectangular parallelepiped, right? And the length of this is dx, breadth is dy, and height is dz. So dv, this is equal to dx dy dz. We put the value of dv. Now we write here the range of the integration, and the range of the integration is clearly z equal to 0 to 3. This is the constant range, and we write here z, this is equal to 0 to 3. And when we put the range of z, then we get the surface as x square plus y square, this is equal to 4, and this is given by this, and this is a circle in xy plane. And if we draw a circle in xy plane and we want to integrate over the circle, then we take, if this is x-axis, this is y-axis, so we get the value of y, this is equal to plus minus root under 4 minus x square. So the range of y, this is equal to minus root 4 minus x square to plus root 4 minus x square. And now the range of x, this is equal to minus 2 to plus 2. Clear? Minus 2 to plus 2, because this is minus 2 0 and this is 2 0, and this is the complete range of the integration. Now we integrate first with respect to z and get, this is minus 2 to plus 2, this is y, this is equal to minus 4 minus x square to 4 minus x square, and the integration is 4z minus 4yz plus z square, and the range is 0 to 3, and this is dy dz, sorry, this is dy and dx. Now we put the range here and get the result as integration minus 2 to plus 2, and integration y, this is equal to minus 4 minus x square to 4 minus x square, and this is 4 into 3, this is 12, and this is minus 4 into 3 into y, this is 12 y, and this is 3 square, that is 9 into dy dz. So 12 and 9 add together, and this is 21. This is 21 minus 12y. Now clearly both the range are of type minus a to plus a. This is minus a to plus a, and this is also minus a to plus a. And we say that this term 12y is odd function with respect to y. So integration of this term must be 0, because we know that the integration minus a to a f of y dy, this is equal to 0 if f of y is odd function, okay, and this is 2 into integration 0 to a f of y when f of y is even function, right? So we put this is equal to minus 2 to 2, and this is integration 2 into 0 to root 4 minus x square 21 dy dz, sorry, dy, this is not dz, this is dx, dy dx, right? And the integration of 21 with respect to y, this is equal to 21 into 2, that is 42 into integration minus 2 to 2, and this is only y, and the range is 0 to root 4 minus x square dx, and the integration is 42 into integration minus 2 to 2 root 4 minus x square dx. Clearly this function is also even function, so we get here 42 into 2, and the range is x equal to 0 to 2, Okay, and we get 84 into this integration is x into root over 4 minus x square by 2 plus a square by 2. This is 4 by 2 into sine inverse x by 2, and the range is 0 to 2. And the integration is 84 into this term is 0, because if we put 2 here, this is 0, and if we put 0 here, this is 0. So this term is 0. Okay, and this is 2 into sine inverse 2 by 2. This is 1 and minus sine inverse 0. So this equal to 84 into 2 into pi by 2, because sine inverse 1 is pi by 2. So our answer is 84 pi. Okay, so the answer of this integration 84 pi, and we use here the divergence theorem, and we also find the volume integration, not the surface integration. Okay, and this is an important application of divergence theorem.